Welcome to part 12 of the DA50 RG aircraft design using CATIA V5. We are designing the last part, and that is the propeller. So let's just dive right into it. There are plenty of images online where you can view the aircraft, but I just went to their page and I can just select one item and zoom in to be able to see a few details that we need for our design. For example, the number of blades. So you can see here we have 3 blades. We have a spinner and we have a hub that is attaching the blades to the aircraft. So the next thing, we can go to the technical specifications. Just type DA50 RG aircraft technical specifications. You're going to arrive to this page. We have the power plant, which has both the engine, the propeller, and the fuel. We have performance, which is very important for aeronautical students because this is where you're going to calculate everything. Now, this one is already calibrated, and the only thing you can do is to reverse design to get some of the initial details that you don't have. And then we have the dimensions, which we used when you are designing the wing and the aircraft. And we have mass and loading. This is like the maximum weight that this aircraft can carry, the maximum weight that we can use when we have takeoff, things like that. It helps to know, to balance between the fuel weight and the passenger weight. All right. So let's go to the beginning. We have the power plant. This is what we are designing right now. The engine drives the propeller. So the engine horsepower is directly proportional to the performance of the propeller. And here we have the Continental CD300 turbocharged, and it has the TOP means takeoff power, MCP means maximum continuous power. So the takeoff power is when the aircraft is taking off, and it's usually higher. And then when we are cruising with the aircraft, it means that the lift is equivalent to the weight and the thrust is equivalent to the drag. And that's where we have maximum continuous power. And here we have the takeoff power. So if you have a notebook somewhere, kindly note down the power. The next thing is the propeller that is installed in this aircraft, and we have the MT propeller, that is MTV12D/21056. We're going to find out what this means, so kindly just note it down, and let's go find this propeller so we can design it. All right, and then the other thing I would like you to note down is the maximum speed during cruise. And you can find it here. Is the first one that is indicated at 16,000 feet and 1,700 kilogram weight of the aircraft. The mean continuous power, which we saw above, the speed is 335 kilometers per hour, and this is true aircraft speed. So you can see some is calibrated CAS and some is calibrated TAS. So CAS means calibrated aircraft speed, and this is at sea level. But when you see true airspeed, it means this is the specific speed at that particular level, at that 16,000 feet. So we're going to use this when we are cruising at 16,000 feet. You can convert this to meters per second. Right here, 335 is 93.06 meters per second. So also note that down as our speed for cruising. The other ones, you don't need them right now. Most of this, I used them when I was calculating the details of the wing, and that is for aircraft students. So we're going to ignore them at this point. Those are the only 3 details we need. So let's go to the propeller. It's the MT propeller. You can Google MTV12 series. And you can either get a page like this for type acceptance report, or you can get the one for EASA, also type certificate datasheet for EASA. So let me show you what you need to get from this particular document. So this is the Propeller Designers page, and it basically shows you the models, and we just need to find the specific model that we have. So if you saw above, we have the MTV12D model. Now, if you come below here, you can see now the documents that you might need to look at when you're designing a propeller. The first one, the first thing to note is that our propeller is a constant speed propeller without feather. And it is also, you can also type empty hydraulic variable pitch propeller or constant speed propeller. The assembly drawing number is this one, P1991. So also note that one down. We're gonna need it to look at the drawing for the spinner. And then these are basically designations of the propeller blade and the hub. For example, the D stands for the flange type. You don't need to worry about that one at the moment. And then the 56 means that this is a wooden blade. So basically, this one is directing you to documents such as the manuals, you know, part list number and all this. And the only thing we need is the manual. So you can come down here and look for it. You can see operating data for propeller. We have maintenance manual. And then we have operation and installation manual for a hydraulically controlled variable pitch propeller or constant speed propeller. And that is E124. So you can try to Google that. You are not going to be able to access the overhaul manual because that one you need to be a certified or a licensed aircraft engineer to access that. But you can be able to get this type of manual. The operation and installation manual is available online. So E124, we can use that. Similarly, if you went to, and you can see here the approved one, you can find Diamond Aircraft Industries here being mentioned around because they use their propellers often. And also, if you are looking at the EASA datasheet, you can also see the models are B, C, and D, and ours is 12D. And if you come down, you don't need all those details about when they were issued. Yeah, so if you need to identify the design, you see here type design definition. This is where you can find whether it is constant speed, whether there is feathering or not. And as I told you before, ours is constant speed without feathering, okay? But you can go through that and try to find the one that is indicated, okay? Now for the description, we have it's a 3-blade variable pitch propeller, as I told you, with a hydraulically operated blade pitch change mechanism. And then we also identified before that it's a wooden blade. So you can see here more details that it's a laminated wood structure with a composite fiber cover. You might need this information if you're going to do analysis. If you're assigning a material to the propeller blades, so this is the material right there, okay? And then for the weight, the dimensions we have between 152 to 210 centimeter. This specific propeller that we are using, the diameter is 2100 millimeters, so 210 centimeters. The approximate weight for the constant speed without feather is 20 kilograms. Not useful for us at this moment. And this is again the hub plus blade combinations. We said the 56 is the wooden blades. For the control system, you don't need it at this point, but you'll find it in the service bulletin. Again, I think you need to be a licensed engineer to access this document. Now, the thing that we need to look here is the speed, the RPM, because remember we found HP, the power in horsepower. Now you can convert horsepower to kilowatts. So for the takeoff power, we had 300 horsepower. And if you convert to kilowatts, it's 220. Now, if you go back to the document that we have here, you can see that, it's 220 point something. If you convert around 221, yeah, 220.6. If you carry over, it's 221 kilowatts. And if you come here for takeoff power and speed diagram, you can see for 221, we have this RPM, and this is what we are going to use in JavaProp. 2340 RPM. The diameter is obviously 210. I've already told you this. You can also try using the maximum continuous power. And the maximum continuous power was about 272. It was 272, right? So you can type 272, find the one that is closest. It's about 200. So again, it fits in this category. And you can see this is the rotation of the propeller. So note this one down, 2340 RPM. Here is the illustrations again to the manuals, and we already identified our manual is E124 for the overhaul, for the operation and installation manual for hydraulically controlled variable pitch propeller. So we'll need this document. And at last, if you want to know what this means, what these numbers means, you can see we have MTV 12D and then you have 21056. So basically 210 is the diameter, all right? That's why we say 210 centimeters. 56, it was for the type. We said it's a wooden blade, okay? But if you want, it can have more or less numbers. And if you want to find out the designation system, here is the propeller designation system. MT, you can see it represents the company. Number 2, it's MTV. V stands for variable pitch propeller. Then 12 here, number 3, is the identification of propeller type. And then obviously here we have the hub designation right here. And that's basically all we need. I'm going to show you how we are going to apply those details. So the last thing that we need now is the diagram. So we are going to go to the operation and installation manual that we saw before. It was E124. And we need MTV12. Okay, it's a long document. I'm not going to go through it, but basically it's just showing you how to install different parts. It also has that section for the blade designation. You're going to find it here as well. Right here, model designation, what MTV means, variable propeller, what have you. It's the same thing that we just did. And the thing that we need from this document is the diagrams which are found at the very end. So this diagrams shows the spinners and the hub, okay? And the one that we need here is at page 98. It was P1991. Remember I told you to write down the part list number for the blade design, okay? It was right here, the assembly drawing for the constant speed propeller. And here it is. And the only thing we are going to deduce from here is the diameter of the spinner. This is the spinner, okay? And the height of the spinner. And if you just zoom in, let's zoom in right here. This is the diameter of the spinner. You can see it's they just illustrated the half of it, but you can see this is the diameter, 338 millimeters. These measurements are in millimeters. And the other thing is the height, which is 441. So you need to make this arc when designing the spinner, and we only need 441 as the height, 338 as the diameter. So note that one down, and let's go now straight to designing the propeller. Now, if you watched the previous episode, at the end, I asked you guys to install this software, JavaProp. It's actually just a Java coding. So basically, we need the blade element theory for us to design the surface of the propeller, because there are a lot of dynamics involved which are interdisciplinary. You know, they are intercrossed, and it's a long process to calculate all those cross sections and to be able to identify the pitch at every single section. So this is a simplified way for us to be able to determine that. And it's very easy to install, very easy to use. So just go ahead and open JavaProp. The first thing we need to enter is our propeller name. So it's just DA50 RG Prop. The number of blades is 3. Then we have the RPM, revolutions per minute, and we saw that is 2340. The diameter was 210 centimeter, but here we need to enter it in meters, so it's 2.1. And then we have the spinner diameter. It was 338 millimeters, so in meters it's 0.338. We have the velocity. The true airspeed that we identified, it was 93.06. So remember, you have to convert to meters per second because it was indicated in kilometers per hour. And then we have power. When we did our conversion, we changed from horsepower to kilowatts, which was 202 kilowatts, but now we need it in watts. So it's 202,830.4 in watts. Leave the shroud options vacant, and then you're going to tick the square tip, because if you go back to the drawings, you can see here we have a square tip, okay? And one thing I need to mention is that the pitch for these blades are calculated at 75% of the blade radius, okay? 75%. And that's why when you come here, you're going to see we are going to get that at 75%. It's the standard one. Next is the airfoil section. And we're going to select this one. The MH126, this airfoil was designed for the root section of a full-size propeller, and it covers a wide range of angle of attack without separation and has the required thickness for the root section. For the angle of attack, I've already input the angle of attacks. It's going to be 5 at the root and 3 for the rest of the sections. Then for a third, remember, this is the root section, this is a third, this is 3/4, and this is the tip region. So for the third region, we're going to select MH112 at 16.2% thickness. The Reynolds number is 500,000 once again, and then leave this angle of attack at 3. This airfoil is designed to follow the root section, and it can cover the typically needed range of lift coefficient for the inboard region. Then for the 3/4, we're going to select MH114 at 13%. And again, the angle of attack is 3. This is mostly designed from 50% outboard. And then we have the tip section. We are going to select this MH120 at 10.3%. Can be 10 or 11. And then you can see the mark number is 0.75. And the reason I selected this is because this airfoil was designed for the tip section of the propeller and can be operated at high subsonic Mach numbers and based on the RPM. So this is what I selected here. And now you can go back and select Design It. And as you can see, you have more details of the propeller, such as the thrust coefficient, the efficiency, because we can never have a propeller at 100% efficient. It can never be. We have too many factors affecting the motion, such as drag, friction, all this. And then we have the torque, the power. Then we have this angle at 75% radius. This is the design pitch, the design angle of attack, the twist, okay? And it is 29.9 degrees. Then we have the pitch. The pitch is usually the distance, the forward distance made by one revolution of a propeller blade, okay? So the pitch is 2.85. Now, using these measurements, if you are confident enough in your design, you can just select this data and go and design one using your own airfoils or something. But if you come to the geometry region, you can see now we have all these. These are sections. Each of these details are at a particular R over R. This means the local radius, okay? At different cross sections of the propeller blade. And the first 4 instances, you can see here, they are left blank because this is where we're going to have the spinner. And then from there, we have the propeller blade. All we need to do is to save this file. For us to be able to import the loft in CATIA, we need the file in .igs form. So if you go to save, I'm gonna choose desktop here, and I'm going to save it DA50 prop.igs and select save. So this one is what we're going to use, okay? So go to CATIA, and then we're going to go to File, Open, select Desktop, and select the file DA50 prop.igs. Here we have the geometry file, the loft. You can see we have all these cross sections. Let me change the property, the graphic properties. Okay, so you can see that the blade is twisted, okay? Exactly how we wanted it to be. If you don't know, the propeller blades are not straight. They are usually twisted, like the same way you see the fans, the fan blades, they are twisted, okay, for it to be able to propel air. So that's why we have a twisted blade. So it goes, the cross section goes twisted. You can try, let's see the front view. Let's see the side view. Yes, so from the side view, you can see how the angle is changing as you approach from the blade root to the tip. And if you show these planes, you can see it's not starting from the origin. We have left a distance here for the spinner, and then that's where the blade starts off from, okay? Now the first thing you need to check if this blade is complete. For example, I mean like the airfoil sections are joined at the very end, because this is it's the same as the wing. We just have these airfoil sections which are twisted, but instead of it generating lift, it produces thrust or torque, okay? So ours is closed. If it was not closed, you can just pick the edges and extrude them until they cross each other, and then cut it. So we can close off this last part. And remember, the generated loft is not like completely touching all these curves. So you're going to hide these curves, and you can now create a boundary of the actual geometry, okay? Okay, we're going to zoom in, select this edge here, create a boundary, and you're going to use now that boundary to fill the surface, okay? And then you can join the two. So select join, preview, and select OK. Now this join, we can again change its properties. Then hide this boundary. And that is how you import the blade loft to CATIA. So now we have this surface. Obviously, we're going to need 3 of these created instances here. So in the next episode, we're going to do that. We are going to complete the hub, so you know how it's joining. And then we're also going to create the spinner and join all this geometry to the new to the other part that we had created earlier. So you need to save this, because as you can see, this is a new part. Okay. So don't forget to like, subscribe, turn on your notifications, get notified when I post a new episode. If you watched this far, thank you very much. Let's continue and finish up this aircraft. So see you in the next part.